Welcome to part 2 from the RTC Tools training, Introduction to Mathematical Optimization. My name is Bernhard Becker from Deltaris, and I'm also external lecturer at RWTH Aachen University in Germany. This is the second part of the workshop of the training. So we have heard reservoir operation, and now it's Introduction to Mathematical Optimization, and this is all tailored with respect to the software of RTC Tools, real-time control tools. And RTC Tools is an open source toolbox for control and optimization of water systems. First, the definition of mathematical optimizations. We understand with mathematical optimization, we understand the selection of a best element with regard to some criterion from a set of available alternatives. Yeah, in equations this looks like this. We have an objective function f, and the optimization task is to minimize this function. It can have several terms that all address certain goals, for example, minimize the spill flow, for example, or maximize power. Usually, this can contain a deviation from a set point. For example, if we have a certain target water level or volume for a reservoir, but can also be a maximize or minimize expression or other expressions. Then we have inequality constraints, G. We use these for physical limits in the system, like the minimum water level in a reservoir or the minimum volume, which can be 0, for example. Volume should not be negative, but we must tell the optimizer that the volume in the reservoir cannot be negative. Can also be the maximum water level. That's the dam height. But also minimum turbine flow. We also here don't want negative flows usually, but also a maximum capacity, and this can also address generation, for example, so power generation. And then the most tricky part are the equality constraints, H here. These are usually the flow equations, for example a water balance. The water balance is an essential part in many water-related modeling, and also this applies for reservoir operations. Now we look only on the optimization itself, the topic of minimization. Let's look at a very simple optimization problem, and this has not so much to do with a water system. It's just an equation I hope you remember from school math. So y is x squared minus 2x plus 1, and it's possible to minimize this with an analytical solution, analytical approach. Find x where the first derivative is 0. So we make the first derivative, 2x minus 2 is 0, and then this leads to x equals 1. And in the plot here you can see the minimum value of this function. This is the square function here, is there, and this is where x is 1, here 0, 2, and there is x. And when we add a constraint, like in our case here, in this example it's x should be between 2 and 6, then we constrain the solution space between 2 and 6, illustrated here with this bar, and then the minimum should be, the minimum value is here, because this one, x equals 1, is no longer feasible. So then we only look at this area here from here to there, and then we have to find the minimum in this range. For reservoirs we deal with a different equation, but not too complex, so this explains why reservoir operations or optimization has also a long history in literature. We have schematization, usually then a reservoir with an inflow and an outflow, and the equation is the change of volume over time is Q in minus Q out. It's a very simple storage equation. It becomes a bit more complicated when we add the power equation. So it's P, the power generation is Q out here, times head difference, gravity and efficiency and the density of water. And here we not only have the discharge but also the head difference. I explained that already in the previous slide, previous presentation, part 1. Inequality constraints, reservoir volume, physical range, dead storage for example, also the dam height limits the maximum volume. And for the turbines we usually have a physical range, the turbine admission, but also the spillway has some limitations, and we use the inequality constraints for that. And if the solution is out of this range, then the problem is infeasible. This often happens that we start with a initial value for the volume which is outside this physical range, and then RTC tools cannot compute. We have also the objective function terms, the F from the previous slides, and here we put in water level, operational range. So these are more operationally motivated goals rather than physical limits. A rate of change for discharge and water level can be specified, for example, but also minimum discharge to ensure water quality during the summer low flow period, for example, or a maximum discharge for flood protection. And we know in certain circumstances we cannot meet this goal, but if we this is just a target, and we can deviate from that, while this is not possible with constraints. So now about local and global optima. Here you see a simple non-convex function, and different to the example in one of the previous slides, there are two minima here and one or two maximum. The thing is that we usually need, or we want to have the global minimum because that's the best available solution, the best what we can do. But an optimizer can also be trapped in a local minimum, and it becomes much more complex if the number of dimensions increase. Here it's a two-dimensional plane, not a plane, a surface, 1, 2, 3 local minima. But imagine we look at multiple time steps, let's say 2 weeks times 24 hours, then each time step adds a dimension, so we have a very high number of dimensions in an optimization problem, and then it becomes much more complex to find the global minimum. So this means we should aim to formulate a convex optimization problem. Now again, back to math. This is our optimization problem, and a mathematical problem is called convex when f is a convex function, here the objective function, g is a convex function, and h is an affine function, which means h of x is 0, or h of x must be smaller or equal than 0, or larger or equal than 0. And this means that h must be both convex and concave, where concave is the opposite of convex. It is affine, and this means that it must have the must be formulated as this is a linear equation. So we have a requirement of a linear equation set, because only convex problems admit global optima. And for us here, this means that we must use linear flow equations. And this is physically not always possible. We can do that for reservoirs, but it can be more complex. And if, imagine we want to optimize for a river stretch with the Saint-Venant equations. This is non-linear, then it's not that easy, but it is possible. And back to the reservoirs. Where does non-linearity come in? Answer number 1, the storage geometry, the geometry of the reservoir. Here's our equation. This is a linear equation, but the water volume in a reservoir is an increasing but generally a nonlinear function of the water level. So it could, for example, look like this. We have here water level, and the reservoir volume is related in a nonlinear way to the water level. Typical solution we apply is that we just use the volume instead of the water level, because with this function we can easily pre-process that. And it's also very typical that for reservoirs in practice there's at least an assumption or approximation of such a water level volume relationship. And here, yeah, this is from a textbook. Here the reason why we have such a nonlinear equation is because the Earth's surface is not so regular, and here you see the elevation lines. And yeah, this is also the volume and the water level here, and the corresponding function is given here. And this is the surface area. This is another nonlinearity. When it comes to evaporation, this becomes relevant. All right. So already mentioned, what can we do? It's not really a linear problem, but we can make it linear because we can choose to work with volumes and flows only. This is very fast, very safe, but it's limited to equations that contain volume and flows. No hydropower, no water level. Already introduced the idea that we use post-processing and pre-processing where possible. So when we are interested in hydropower, if we're interested in hydropower, we can just post-process that from the computation results. But this means that we cannot so easily include a hydropower generation goal into the optimization. We can also choose to approximate those parts that are nonlinear with a linear function. So we compute it linear, although it's not linear, and this comes with inaccuracies, of course. And then when we look at this green line here, this we consider as the truth. A linear function could look like this. Yeah, this is not exactly the same. And a bit better is when we use piecewise linear approximation. Here, these red lines. Then we split the nonlinear function into linear pieces, and we apply linear behavior for sections. But this limits the inaccuracy, but it's still a bit inaccurate. And it's quite fast, but this brings us into another issue because it adds Boolean logic to the optimization. Yeah, and then this is the subject of the next slide. We can also apply a homotopy technique. But let's first look at the hydropower generation. Here with this equation, P is a function of discharge and head difference. Then Q and head difference are usually the optimization variables. This means that P is a nonlinear and even non-convex function of Q and delta H. So we can choose for optimization variables and goals such that we have a nonlinear but convex formulation. A typical common approach is that we set the head difference as constant, but this means that we have no longer an incentive to keep the water level high for the reservoir, and this is not what we do in practice. If the focus is on hydropower, we aim to keep the water level high, as high as possible, and then we can also choose to go for maximize power as an optimization goal, but not produce a certain power amount. And here are some illustrations. Here's the head difference and discharge, and the function, yeah, here illustrated with isolines, so contour lines and colors. Here's the maximum, so this is still convex. When we add the turbine efficiency, here the hill chart to it, these two combined is this plot, and then here's the maximum. And yeah, we can flip that to invert that such that we have a minimization problem. So the optimizer can find this point here, the maximum power generation, but But if we say the power generation must be this value, then there are so many solutions. The solution is no longer unique because every point on this ISO line here would be a valid solution, and this is not the optimizer do not really enjoy such a task, and they cannot find a local optimum in this case. Then already mentioned the homotopy method is a novel approach. We are working on a paper currently. The functional principle is that we bend the equation from linear towards nonlinear with the help of a theta. So here again the power equation, G rho eta, and here Q turbine and data H tilde. This to start with, theta is 0, and during the optimization process we move theta from 0 towards 1, and then we get from this linear simplification with constant head difference move towards the real head difference here during the optimization process. This gives accurate results fast, but it's not yet ready for all water-related equations. We have only applied this so far for the power equations and the water level storage relations for reservoirs. And then of course there are a lot of heuristic approaches, but they come not with a guarantee for a global optimum. The functional principle, there are so many. For example, a genetic algorithm is inspired by natural selection. There are so many others, pattern search and whatever. This is they are very frequently used, but the fact that they don't guarantee a global optimum means that we might run into stability issues. A little change in the inflow towards a reservoir can lead to a completely different optimization result. So we say this is not really suitable for an operational use, where we use the optimization during a daily duty for reservoir operations. And they are also comparatively slow. Usually the gradient type optimizations, they are much faster. But here's some examples about the homotopy. The green line, that's the homotopy approach, and here you see discharge over time for a reservoir, and here day-night pattern of discharge for power generation, and here you see a little increase of discharge, and this accounts for the reduction of head difference that comes with the release of water from the reservoir. And the linear and the piecewise linear here in black and red cannot account for that, because there the head difference is always set to a constant value, and only the homotopy is able to represent this increase of discharge. And here's a generation, a load balance request, a generation request behind. And then here this is also related to the homotopy and piecewise linear. We see here the power independence of the head difference. So when the head difference change, the homotopy approach changes the power. But with piecewise linear we have some domains. So from 15 to I think it's 18, the head difference is constant. Then it jumps to another head difference. Head difference is constant. It jumps to another domain of head difference, and consequently the power is also constant, the same for this domain. So we have this staircase approach here, and if we use a fully linear approach, then the head difference, maybe it's 25, then the power is always the same, whatever, no matter how big the head difference really is. Okay, this may be enough for the nonlinear linear discussion. Now to the multi-objective optimization. Multi-objective means that we have different objectives and not only one. Suppose we have the following goals: keep the water level within bounds whenever possible, maintain a minimum spill flow for fish migration if possible, and apply the best effort to track the hydropower generation request. So now the math let f denote the set of functions that encode these goals. Then we have minimize all objective function terms for I, 1, 2, 3, subject to a set of constraints and our flow equation. How to solve this with these three different goals? That's important. Not so much the flow equations. With a mathematical expression, the solution x star of the problem is Pareto optimal if there's no x star star, such that for all other solutions the function term is smaller than it would be for the x star. And for all I non-equal j, we have the function of x star star smaller than f I x star. Now this is mathematical expressions. In words, easier to understand. Pareto optimality implies that no goal can be improved without making another one worse. So there's no x star star that gives a better solution for the same function term, but also not a better solution for other objective function terms. Or other goals. Graphical representation is the Pareto front as a set of all Pareto optimal solutions. Here we have two goals because that's much easier to plot. If we improve towards goal 1, 1 would be the best. Then we have nothing for goal 2, so goal 2 is not met at all. And we can also choose to go for goal 2, perfect match, but then goal 1 has 0, so that's completely not obeyed. And the Pareto font illustrates the compromise between these. And the weighting method is used to transform the multi-objective problem into a scalar problem, and we introduce a weighting factor, and this weighting factor allows us to tune which goals get a bit more emphasis than the other. But the question in practice, we have experienced that, is how to pick the weighting factor lambda. This is a matter of choice. So we can choose them and move a bit towards goal 1 or goal 2 or 3, and this becomes much more complicated if we have more goals than 2 or 3. So they are somehow arbitrary, but then the optimization result is somehow arbitrary too. And yeah, so we can play around with the position of the Pareto front and the trade-off. But this does, not really solve our problem, or it's not really helpful in practice. So we came up with the lexicographic goal programming. It's also a quite common approach from literature. We transform the multi-objective problem into a sequence of scalar optimization problems. So instead of one with the multiple objective terms, we just solve three optimization problems. Each for each of the goals, we solve one optimization problem. So first we order them. The most important comes first. Keep the water levels within bounds, such as much as possible. Second, maintain a minimum spill flow for fish migration, if possible. And third, best effort to track the generation request. And then the idea is just that we minimize for the objective function term 1 to get a minimum objective value for the first. Then we do the same for the next goal, objective function term 2, but we add constraints from the previous optimization, and we introduce what we achieved here as constraint to the second. And for the third we do the same, but then we have additional constraints from the first and from the second optimization, and so forth with goal number 4 to n, whatever. That's all, and we will learn how this works in practice in the next part of the presentation. Thank you for listening. See you later. Goodbye.